Let's use the simplex method in Tableau form to maximize the profit of the company Optimal Hummus. Recall the model in simplex form for the hummus problem. The simplex method starts with an initialization step in which we set the original variables to 0. Then we check if the solution is already optimal. If not, we repeat 4 steps until optimality. In step A, we select the entering basic variable. In step B, we determine the maximum possible increase of the entering basic variable such that all other variables remain non-negative. The basic variable for which its value is reduced to 0 is the leaving basic variable. Then in step C, we determine the incumbent solution. In the last step, step D, we check whether the incumbent is optimal or not. The initial simplex tableau for the hummus problem has a header with all variables. RHS stands for right hand side and BV is short for basic variable. The tableau has 3 rows, 1 for each of the basic variables. As Z is not really a basic variable, we have separated this row from the other rows with a line. For this initial incumbent, S1 and S2 are the basic variables, and X1 and X2 are the non-basic variables, so X1 and X2 are equal to 0. The S1 row represents the equation to calculate the value for basic variable S1. 2 times X1 plus 4 times X2 plus S1 equal to 240. So because X1 and X2 are equal to 0, the value of S1 is the value in the right-hand side column, 240. Likewise, S2 is equal to 480 and Z is equal to 0. This gives an initial basic feasible solution with both X1 and X2 equal to 0, S1 equal to 240, S2 equal to 480, and Z equal to 0. To see whether our incumbent solution is optimal, we check the row of Z, which gives Z equal to 5 times X1 plus 7.5 times X2. Z can obviously be improved by increasing either X1 or X2 from 0 to a positive number. We conclude that the incumbent is not optimal because the row for Z in the tableau contains negative numbers minus 5 and minus 7.5. Because Z can be improved the fastest by increasing X2, the entering basic variable is X2. So the entering basic variable is the variable which has the most negative coefficient in the row for Z in the tableau. Next, we determine the maximum possible increase for X2 by choosing the so-called minimum ratio test. The ratios that we consider are the right-hand side of the S1 row divided by the coefficient of X2 in the S1 row, and the same ratio for the S2 row of the simplex tableau. The minimum ratio of these two ratios is 60, so S1 will be the leaving basic variable. Now we determine the incumbent solution by applying row operations such that each basic variable appears in exactly one row with coefficient 1. The intersection of both the row and column of X2 is called the pivot. By dividing the S1 row by the pivot, the row is transformed to an equation for entering basic variable X2. So as coefficients, we get a half, 1, 1/4, 0, and 60. S1 changes to X2 in the column of basic variables. Next, we use the pivot to eliminate the X2 coefficients of the other rows. So we add the X2 row 7.5 times to the Z row, you can pause to check the calculations, and subtract the X2 row 5 times from the S2 row. For the incumbent solution, both X1 and S1 are non-basic and thus equal to 0. X2 is equal to 60, S2 is equal to 180, and Z equal to 450. To test if the current incumbent solution is optimal, we check if the Z row has negative coefficients. Because it has coefficients minus 1, 1/4, we need one or more additional iterations following the steps of the simplex method.